Great. So light is now going to speed up. Let's keep it similar to the problem that we did before, and we'll have light going from water to air. So light will speed up going from water to air. And we're going to do the same sort of thing as what we saw before, except a little bit in reverse. Here's the boundary. Let's have this be the air, this be the water. We need our light starting in the water. So I'm going to draw a normal line. Let's pretend all of our rays are going to hit there at that intersection. And once again, we're going to do a 20, 30, 40, and 50 degree angle of incidence. Let me just mark those off. 50. And once again, we'll do the same thing. The black ray will be the 20 degree angle of incidence. Okay, I think I went, which way did I go? Black, green will be a 30 degree angle of incidence. The blue will be my 40 degree angle of incidence. My red will be my 50 degree angle of incidence. And this time I know what I'm doing, so I'm going to put the math down here. And so let's do this. You know what we're doing here. So theta 1 is going to be 20 degrees. Theta 1 is going to be 20 degrees. 30 degrees, excuse me. Theta 1 is going to be 40 degrees. Theta 1 is 50 degrees. And I'd like you to calculate the angle of refraction for each of these. Stop the video for a second, and then when you come back, I'll start doing that work with you. So started out pretty easy, right? So let's take a look. I'm going from water to air. So if I'm doing Snell's law, N1 sine theta 1 is equal to N2 sine theta 2. Okay, N1 here in each case is 1.33, so I'm just going to fill that in my template. 1.33. Then this is sine 20, sine 30, sine 40, sine 50 is equal to going to air in each case. And then I'm looking for theta 2. All right, so let's see what we got in each case. Theta 2, 1.33, sine 20, second sine, answer, and got 27.1 degrees. Theta 2 is equal to 1.33 sine 30, second sine, oops, 1.33 sine 30, sine, answer. You got 41.7 degrees. Theta 2 is equal to 1.33 sine 30, shift, answer. Oops, I just did the same one. 1.33, 1.33 sine 40, second sine, answer, 58.7. Let's just stop there for a second. We know when we speed up, we should bend away from the normal. So far, let's see what we've got. Oh, good. 20 became 27, 30 became 41.7, 40 became 58.7. So let's just draw those in. And yes, you're probably very frustrated with me that I stopped where I did, but just go with me for the moment. Okay? So there you go. The green one is going to go, and that's going to go to 41. So that goes there. Boom, and then the blue one is going to go to 58.8. So 58.8 is about there. Boom. I think it's pretty easy to see there that there's my black ray, which is incident at 20 degrees, and this is larger than 20, right? It's bending away from the normal. Here's the green one, bending away, larger, and then here's the blue one, bending away, larger. Oh, good, well, that happens. So in each of these cases, theta 2 is greater than theta 1 when you speed up, which is nice, it bends away. If you notice here, as theta 1 increases, so does theta 2. So this is another increasing relationship. But now let's look at the nature of that increase, going from 20 to 30 to 40. We went from 20 to 30. That increased by 41.7 minus 27.1. That increased by 14.6, going from 30 to 40. 58.7 minus 41.7. Oh my God, 17. So not only is it an increasing relationship, but as theta 1 increases, theta 2 increases increasingly. Well, that's a fun sentence. So as theta 1 increases, theta 2 increases increasingly. Okay, so now you're all saying, well, hold on, what about this one here? So when you did this one, what'd you get on your calculator? Hopefully people are saying things like, hold on, I got a math error. Well, I'm not hoping you say that, because math error means, you made an error in math. The question is, did you make an error in mathematics? And the answer is no, you didn't. That is the plugin for that. What actually happens here? Well, when we look at 1.33 times the sine of 50, what you get is 1.019 is equal to 1 times the sine of theta 2, right? And as you and I all know, the domain of the sine function, the range of the sine function is between -1 and 1. And so this is falling outside of that range. Therefore, what angle would produce that as its sine? The answer is there is no angle. So we don't want to say math error. What we want to say is the more formal, correct mathematical conclusion here is DNE does not exist. There is no angle that exists whose sine is greater than 1. That's just impossible based on how the sine function is defined. So what does that mean physically that theta 2 is DNE? Well, what's theta 2? Theta 2 is the angle of refraction. This says that the angle of refraction does not exist. Well, why might the angle of refraction not exist? Well, that's the fun of it. The angle of refraction doesn't exist because this ray doesn't refract. It, in fact, never gets transmitted into the air. So what happens to it? Well, first off, let's just see that for 0 degree angle of incidence all the way up to like 40 something, that this thing is refracting, but there must be some region of angles, incident angles, that it doesn't refract. And notice that these are the larger angles. So we're gonna come back to this in half a second. I just wanna show you physically that this happens, right? Those of you who are observant might have seen it before. Here we go. I have a 0 degree angle of incidence, boom, boom, right? And what we're concerned with here is not this transition, but this one here. Why this one here? Because we're talking about when the light is speeding up, when it's going from a higher end to a lower end material from lucite into air. And we're seeing nothing here, nothing here, nothing here, nothing here. Well, the way I'm going to do this is I'm actually going to come over here, and there you go. Look at that by my hand. There is no light that's coming out here. Look at that very large angle of incidence, and you can see the light reflecting inside the object. It's trapped inside the object. All of the light is being reflected there, right? And that happens, hold on, let me just like change up the geometry. Boom. There you go. All the light's coming out, and now it's reflected. So it doesn't happen at all geometries. It only happens at large angles of incidence as you go from a higher end material into a lower end material. We're going to give a name to this. This is going to be called total internal reflection. Okay? It doesn't always happen, but it happens, or can only happen, when you go, or not go, when you attempt to have light pass from high end or higher end materials to lower end materials, right? Meaning when the light is trying to speed up, and then only at larger angles of incidence, right? And what happens here is that the light does not refract, it reflects. And we call it internal reflection because you can kind of think of it as the light getting trapped within that material. All right, now I dropped my piece of paper, so I gotta find it. Awesome. Here we go. So here we go. I know mathematically I get total internal reflection if I find out that theta 2 is dne. So mathematically, if I get theta 2 is dne, I know I've gotten the total internal reflection. So that's this one here. So what happens to it? Well, we said it reflects. So what direction does it go? Well, if it reflects, it obeys the law of reflection. So that means that if this is a 50-degree angle, this has to bounce off that surface at also a 50-degree angle. Boom. All right. So now what you must be thinking to yourself is, okay, well, sometimes when I'm doing this, it reflects, sometimes it refracts. There must be some sort of boundary line between those regions. And there is. There is something that is called the critical angle. And we're going to call the critical angle theta c. And its definition, you got to be very careful about this definition. It is the maximum angle of incidence that still causes refraction. Okay? Well, what is the most that something can be refracted by? Well, here, if I have a 0-degree angle of incidence, I get a 0-degree angle of refraction, meaning it doesn't refract. And then the angle of refraction can increase from 0 all the way to 90. I can have a light ray go from this material, go into the air, but then skim along the surface at an angle of 90 degrees. So another way to define the critical angle is it is the incident angle that causes an angle of refraction of 90 degrees, okay? Such that if theta 1 is less than or equal to the critical angle, it refracts. If theta 1 is greater than the critical angle, it reflects. So for our example here, going from water into air, let's calculate the critical angle. Well, I'm just going to use Snell's law. And really, if I'm going to be super formal about it, what I should be doing here is I'm going to take the limit as theta 1 approaches the critical angle. So watch what happens here. N1 here is water. And then theta 1 becomes the critical angle because by definition, the critical angle is an incident angle. And then N1 is, or N2 is 1. And then sine, if I'm at the critical angle, the angle of refraction is 90 degrees. So if I plug that into my calculator, and calculate that angle, I get that theta c is 48.8 degrees. Oh, look at that. 40-degree angle of incidence is below the critical angle. It refracts. 50 is above. It reflects. It all sort of worked there. There we go. So, well, what happens if I try to go from air into water and I try and calculate the critical angle? Well, that becomes 1 sine of theta c, if I do that same limit, is equal to 1.33 sine 90. And if you do this, you get theta c equals dne. Well, what does that mean? Well, that doesn't mean what the dne when theta 2 is equal to, because this said the angle of refraction doesn't exist. This says the critical angle doesn't exist. And the critical angle, folks, is the maximum angle of incidence that causes refraction. This says all angles of incidence cause refraction. Oh, okay, well that makes sense because I'm going from air into water. I am slowing down. Well, why does that work? Why do I get critical angles speeding up but not slowing down? If we go back to these pictures, they kind of explain it to us. Because if you look at this, actually, let's go to the picture for when I'm slowing down. Find that from the notes the other video as I speak slowly and try and find that piece of paper. Here we go. Notice here, because theta 2 is always less than theta 1, as theta 1 increases from 0 to 90, theta 2 is going to increase as well, but it's never going to get to 90 because it's always got to be less than theta 1. So there's sort of like enough space. But here, because theta 2 increases faster than theta 1 does, I'm going to run out of these angles before I run out of these angles. So that's why it happens when I speed up and not when I slow down. So, total internal reflection. The last thing I want to say about this is an application of total internal reflection. Fiber optics. A fiber optic cable can literally trap light in it, bouncing back and forth. The light can't get out because this material is of higher N as what this material is. We can use that in order to guide light where we want it to go. That's where optical computing is heading, folks, if that's something that you're interested in. So that's a great application of total internal reflection.